Good morning, good afternoon, good evening, ladies and gentlemen, wherever you are in the world. My name is Tim Collins, and I am the Secretary General of the International Stainless Steel Forum based in Brussels in Europe. It's afternoon at the moment, Brussels time, but I know for some of you it will be early in the morning. Maybe for a few people it's later in the evening. So we're having a look today I should say, rather than this afternoon, on a discussion concerning future mobility, which I've subtitled Dumping Fossil Fuels to give the webinars a little bit of impact. Before I start, just a few practical housekeeping type matters. So regarding the presentation, everybody who has registered for the webinar will receive a copy of the presentation emailed to them. So you don't necessarily have to take notes during the presentation. Equally, the recording of the presentation with my narrative will be placed on YouTube. So if you so desire, you can re-watch it at your leisure and equally share it with other people. And finally, regarding questions, we'd like people to log questions through the chat facility. We will take questions at the end, and if we don't have time to answer all questions, anything we don't discuss during the 1 hour session today will be responded to with an email answer. Furthermore, on the subject of questions, if anybody wants to pitch questions after the webinar, please do so. My email address is shown on this opening slide, which obviously will be sent out to everybody, and we're happy to answer questions a little later in time. So I hope that's all clear. So here's the agenda for today's session. There's lots of topics we're going to sort of walk through, but really I'll open things up by a brief introduction, followed by a view of mass urbanisation and the current mobility situation. Then we will talk about future forms of vehicle propulsion and why hydrogen is or should be an optimal mobility choice, and a bit about hydrogen mobility development and the associated supply chain. And then we'll start to move on in the final third of this to look at materials to support hydrogen mobility particularly. We'll look at the key processes and then at the end summarise and conclude before questions. So that whole presentation part should take between 40 and 45 minutes. So I hope that's okay. And we'll move forward with a fairly stark introduction. It's clearly fair to say that we have been using and now overusing fossil fuels, and it is destroying our planet, it's seriously harming our people, and that's through a variety of features, whether that be pollution that we see and witness every day, climate change, which we know is unabated at the minute, and extreme weather events. And if we just pick up on one of those extreme events, Hurricane Harvey back in 2017, whilst there were relatively few deaths, less than 100 as I recall, there were 7 million people who were directly impacted by this in a very severe and unfortunate way. And the total recovery costs for this one event were over 170 billion US dollars. And these are frightening numbers without a doubt, and Hurricane Harvey is one example. But what's interesting is the mobility sector in its entirety, so all forms of transport, contribute 28%, so approaching of a third of our total global greenhouse gas emissions. So this sector contributes massively towards the pollution and climate change and these extreme events. So with that in mind, it's quite interesting to do a simple comparison early in this presentation. And on the left-hand side of the chart, you have an internal combustion engine vehicle, and on the right-hand side, a fuel cell vehicle. And I've only chosen two alternatives to show here so that the chart is relatively easy to understand. Now, on the y-axis here, we have what's known as an energy index value. So if you extract oil or you create an energy source, you start off with 100% of your energy or 100 units in this index value, and that's available to use. But before you can use it, there are energy losses. And in the case of oil, it's through the refining and conversion process and ultimately transport. And that's a relatively small loss in the scheme of things. But then when you actually get the gasoline into the car, you lose a huge amount of energy. The available energy that's doing real work falls to just 13%. So the bulk is lost in engine inefficiencies and transmission inefficiencies. And that's a variety of impacts. So a huge loss, even though we think this is quite an acceptable and efficient system. By comparison, when you look at a fuel cell vehicle on the same chart, the losses are there. The energy loss in terms of hydrogen production and conversion is bigger, but then the energy loss in the vehicle is much, much smaller. And actually you get almost 3/4 of the energy available for moving the vehicle and its contents. So in this scenario, we see that it's not about the absolute numbers, it's about the relative differences, that we've got a system that we've lived with and loved for many, many years, but it's not that efficient. And there is a system available, and it's one of several that offers a much higher efficiency. Now, moving on to think about mass urbanisation, because this is where a lot of our vehicles are being used in these urban settings. We'll look at mega trends in greenhouse gas emissions. So let's start to think about mega trends first and foremost. So we have almost 8 billion people living on the earth today, over half of whom are living in urban settings. That's 4.3 billion people. The growth in population is fairly static at the minute, around 80 million new people per year. But that still means that by 2050, in under 30 years, the population is expected to reach over 10 billion people. And of those 10 billion people, more than 2/3 will be living in city environments. So we're talking a huge number of people. And what's interesting is those city environments only occupy around 3% of the land mass of the earth, but consume 70% of the energy needs and generate 80% of the economic output. So cities are really important to us, but we have to learn to do things perhaps a little differently. And one of the key reasons for that is the transport sector and how it pollutes today our urban settings, not just our urban settings, but those particularly. And as we said, 28% of global greenhouse gas emissions are attributable to the transport sector, and air pollution directly accounts for about 4.5 million deaths globally per annum. Now, the World Health Organization have equally looked at some of these pollution issues and said that 80% of urban dwellers are exposed to high levels of air pollution. And that's pollution against the PM 2.5 standard of 10 micrograms per meter cubed. And this is small particulate matter in the air of diameter less than 2.5 microns. So very small particles, but all these particles come from fossil fuels. So we understand that this will lead to serious respiratory health problems, but at the same time, cities are here to stay. So if we are to accommodate this increasing population in urban settings, we must decarbonise our cities. To keep our heads in the sand and just keep using internal combustion engines is something we can't sensibly consider as a global society. So let's move forward and consider mobility and transport emissions more generally. Today we have about 1.4 billion vehicles on the roads around the world, and we're not including in that number designated off-road or heavy construction vehicles. And together this 1.4 billion vehicles emits about 2.3 billion tonnes of carbon dioxide each and every year. And the worrying feature is that's not going to go away unless we change something, because by 2035, the number of vehicles is expected to reach 2.3 billion. And of that, light duty vehicles will be about 95% of the total. Now, if we look at today's situation, just 2.5% of total vehicles are in what we class as the greener category: battery electric vehicles, fuel cell electric vehicles, or the hybridized electric vehicles. So we've got a long way to go to reduce our carbon emissions over the next few years. Now, equally, whilst most regions of the world have put emissions targets in place, the view of the scientific community is that we must cut our carbon emissions by 80% to stabilise climate change, and that's more than most regional targets around the world. So that means that different form of propulsion, whether it be for personal vehicles or for regional transport, urban transport, it's needed, and it's needed now and needed quickly. If we have a reflection, and this is one of many graphs I could have presented. So this is the European Union tracking of CO2 transport emissions since 1990, and the solid red line shows the growth in millions of tons of CO2 equivalent emitted on an annual basis. The dotted red line is the trend associated with that pattern. So there is no doubt that we're on a worsening trend. And if I'd presented America or Asia, it would show the same pattern. Now, the two horizontal lines, the blue line is the 2030 European Union target, and the green line is the 2050 target. And these represent 30% reduction compared to now in the case of the former, and 60% reduction compared to 1990 levels in the case of the latter of those two. But we should note that the scientific community believe this is still not enough. So whilst these targets are credible, they're way off what we need to achieve to safeguard our planet and preserve its longevity. Now, I'd also like to reflect on this data in a slightly different way, and there are many ways to look at CO2 emissions, and this is not just transport, this is everything. And you've got on the y-axis annual tons of CO2 per head of population. So this is an attempt to normalise country-wide data. And then along the x-axis, you have many countries, not all of the world. And the horizontal red line is the Paris Agreement target level. And what's interesting in this graph is not the absolute numbers, it's broadly the gap for most countries against the target. The gap is just huge, and that's what we have to change. As I said, there are many ways of presenting this data. No way is perfect, but because you can argue, hey, some countries have really big geographies to contend with, populations are very much polarized into urban settings, so we're not always comparing apples with apples, so to speak, but it's an indication of how far we have to move that's important from this data, not the absolute values. So I think we should hold that thought in mind. Now, if we move forward and think about practical future forms of propulsion, there are four interesting pictures here. The top two are internal combustion engine vehicles. And apart from going, approximately 100 years or so ago, from something that's not too pretty, even though it may have been considered attractive at the time, to something that is very pretty in the top right, the technology hasn't really changed. It may have got a little bit more efficient and may look a lot nicer, as we've said, but it hasn't really changed. Whereas at the bottom, you've got two quite different technologies, the hydrogen fuel cell system in the bottom left and the pure battery electric system in the bottom right. And these are really more innovative approaches, but none of these systems are a perfect solution today. It's just a question of, are some better than the other? So if we move forward and just look at the current greener three in the list of future forms of propulsion, and this is a very simple, a cheap and dirty way of assessing the positives and negatives of these three vehicle types. So at the top, we have battery electric vehicles. As most people know, it's powered by electricity from a battery array within the vehicle itself. The positives are it doesn't produce any emissions. And I think we could say as long as green energy is used to make the electricity, it's really a zero emission system. But we know that's probably not quite the case today. This is a very practical solution in urban short distance settings. But on the downside, it has a limited range. That is changing all the time and will definitely get better. Today, much of the electricity comes from fossil fuels, so it's not completely green. The charging infrastructure can be problematic. For people that live in houses with their own parking spaces, that's okay. In apartments, it becomes more complicated. And if this technology really takes off, the pressure on raw materials is likely to become quite extreme. So there is another supply chain consideration there on the downside of these vehicles. If we move on to the hybrid electrics, we know we have power from two sources, electricity from a battery array and an internal combustion engine. This is a halfway house. It offers good driving range. It's practical in all settings. It's seen as a tax benefit in many cases, and whether that's a real positive or not is a questionable feature, but they are gaining traction because of that, particularly that tax benefit. On the downside, the electricity is primarily coming from fossil fuels. It still relies on gasoline, and it's relatively high unit cost today. And then at the bottom of this assessment, we have the fuel cell vehicles. So here you have a dominant hydrogen power system with a small battery array to support the hydrogen fuel cell until it reaches steady state operating conditions. Water is genuinely the only emission. It has or offers a good driving range, and that's developing again all the time, rather like the battery vehicles. The hydrogen can be purely produced from green energy. I'm going to talk about that in a little while. And on the downside, it's high unit cost, and that would have to change to make it appeal to the masses. And not everybody is convinced by the technology, and that's for a variety of reasons. But I'll talk about some of those issues a little later. However, if you then consider these three vehicle types against their life cycle emissions, we get an interesting picture. And internal combustion engine vehicles have the worst life cycle emissions currently. And typically over the life of a vehicle, you're producing somewhere between 36 and 40 tons of CO2. What's interesting is 70% of those emissions come from the engine and the tailpipe. And it's only 30% associated with materials used for production. And we already know this is not a terribly efficient system, so we perhaps shouldn't be surprised about the magnitude of those emissions from the engine and the tailpipe. Battery electric vehicles, by contrast, have a much, much lower life cycle emission level of 25 to 27 tons of CO2, and roughly half of those emissions are associated with the battery array production, the balance with materials primarily to do with production. And then at the bottom here, we have fuel cell vehicles. And as long as you can source the hydrogen from green energy, this has the lowest life cycle emissions, somewhere between 16 and 18 tons. So half of the internal combustion engine. And of these emissions, a little over a third are associated with hydrogen storage, the fact that it's compressed and cooled. And 30% of the emissions come from the fuel cell and battery production. So in some respects, a similar dimension to the pure battery electric vehicles. But this is an interesting comparison that really says there's another way to think about vehicles and recognize that vehicles have a relatively short life here. We're looking at sort of 10 to 13 years typically. These are not huge life items or assets in our sort of array of desirable things in our life. Now, if we take those thoughts and move forward, I would argue that hydrogen becomes a very optimal choice for mobility for a number of reasons. One, that electrolysis of water using electricity is the leading production system for the production of green hydrogen. There are other ways of producing hydrogen that are definitely not green. But if we're thinking about green hydrogen, then water electrolysis is the leading system. And hydrogen is actually well aligned to green energy sources, particularly solar and wind, because when those energy sources are available, you can convert water into hydrogen, which you can then store very easily. And by the use of an electrolysis system, you can really decouple the energy supply chain, which is much more difficult to do with traditional power generation systems. So you generate hydrogen when the wind or sun are available, store the hydrogen, and then when you need it on demand, you can convert it back into electricity. So you avoid this difficult feature of grid balancing. And this approach fits perfectly with the mobility sector. And the fuel dispensing process is really no different to that for internal combustion engine vehicles. So you get over the sort of charging infrastructure dilemma that comes with battery vehicles. And as I've said, battery electric vehicles are not yet fully aligned to green power, but that will change. So that's something just to be aware of. It will get better for the battery vehicles. If we then consider the emerging conclusions from Hydrogen Mobility Europe, and they have several phases to their development of hydrogen in mobility, there is no doubt that hydrogen can be generated through a range of zero carbon green energy routes. It also allows countries to have independence from energy imports, so it gives them more stability in that respect, and that in itself creates an opportunity to promote wider economic growth in each country. It's clearly a safe and very clean fuel, and no major incidents have been reported from a safety perspective over the last 6 years, which is great to hear and be aware of. It's also fair to say that fuel cell vehicles can meet the needs of all operational users. Clearly, they are most suitable for zero emission vehicles driving over long ranges and with heavy use applications. But equally, there's no reason to see why for light duty vehicles, they are not a valid proposition. They are very valid in this context. The weak aspect of hydrogen as a choice at the minute is the refueling infrastructure. And it does need rapid development, and that requires local government and administrative support and incentives, because without that, consumer confidence will not develop. So that's a clear conclusion from the European guys driving hydrogen mobility forward. But how does hydrogen actually fit against a mobility development? And this is a Hydrogen Mobility Europe chart. And on here, on the y-axis on the left, this broadly looks at the asset weight of different vehicle types. And then on the x-axis on the bottom, this is the driving range, or the required driving range, based on one full tank of fuel. And the size of the bubble is really reflective of the size of the market share that hydrogen can actually take. And what you see in the middle ground here is that there's a number of vehicle types: medium and large trucks, buses and coaches, medium and large cars and vans and small trucks, where hydrogen can shift into somewhere between 40 and 50%, or maybe a little more than 50% of the total vehicle mix. For things on the extremes here, motorcycles at the lower end and regional trains, it's likely to be a lower proportion that shift into hydrogen as a fuel system. And that's for good reason. If you take trains as an example, we already have many electric train systems in place with the overhead wires. So it's unlikely they would switch to a hydrogen system. It would just be more a focus on green electricity production to supply the electricity to those trains. But it's that middle group of personal transport, goods transport, and sort of public transport that really have the opportunity for hydrogen to develop well. Now, if we now move on and consider the hydrogen supply chain, what I'd like to do is describe this in 4 supply chain steps, or echelons as they're correctly termed. And here we have echelon 1 combining 3 features: electricity production, water electrolysis, and then the post-production storage of hydrogen. And these steps have the opportunity to be combined into a single system. But also the echelons can be combined. As we walk through them, I'll explain this. If we look at echelon 2, this is the movement of hydrogen from the production site to the refueling station. And if you didn't have to do that, you could just remove that. It is a defined waste. It's not a needed process. Echelon 3 is the refueling station storage and then the dispensing of hydrogen. That's very similar to how we fill tanks with gasoline today. And then the last echelon is the vehicle storage, so the tank on the vehicles and the usage of the hydrogen whilst we're driving. Now, the next slide, if I move on to that, breaks those 4 elements down. I'm not going to go through this in detail. This is a reference slide just to show the key elements. But what is possible from this is that you can take this concept and shrink it into 2 key elements. Take away the transport by modularizing production and refueling into a single unit, and then you make your supply chain much simpler. So the notion of producing hydrogen at a refilling station, storing it and dispensing it when required is very interesting and is being prototyped right now in several countries around the world. So this would simplify the supply chain dramatically. So why do we believe, or why do I believe, hydrogen mobility is important? Well, it is the zero emissions solution, particularly when we're thinking about hydrogen from green energy sources, and it fits well. Refueling is really fast. It's the same as a gasoline refueling system, pretty much. We get the long driving range, and this is developing all the time. Currently, we're in the 500 to 700 kilometers range. 1,000 kilometers is on the not too distant horizon. Hydrogen refueling station can be fully integrated with a production system, and these prototype units are already being trialled in various countries around the world, as I said. And broadly, they have a 20-feet container footprint, so they're not huge. And hydrogen does provide a clear solution to the major challenge we have, that transport is the only sector with rising CO2 emissions. And if we do nothing, that will continue to rise. So let's move on now and get into the sort of material considerations to support hydrogen mobility. And our primary focus today is on these 4 elements of the supply chain: production, transport, dispensing, and usage. And whilst there are many material choices available, we're going to focus on metals, alloys, and composites primarily, and I'll use a few examples to illustrate that. So we're going to consider 4 materials. Aluminium, it's a very well-loved, resilient metal. It has many fine attributes. It's lightweight, it's fully recyclable, has many, many uses that we're all familiar with. I'm going to consider 2 stainless steels, and you not expect me to do anything other than representing the stainless steels industry in throwing in some stainless steels in there. And I'm considering in this presentation austenitic stainless steels, which is the most common stainless steel family, and most people will be familiar with austenitic stainless steels in the form of cutlery, pots, pans, domestic appliances, etc. They are considered as expensive, but they have a number of very unappreciated attributes. We'll also look at duplex stainless steels, arguably the new kid on the block. This is a high strength, high corrosion resistant steel, so it gives the opportunity for lightweighting. It's only been around 80 odd years, but it still is relatively unknown for many people. And then we'll also put alongside that one of the plastic community products, fiber reinforced plastic, which is a very versatile material, high strength, very lightweight, some really solid attributes, including corrosion resistance. Now, what I'd like to do is look at those against a series of desirable attributes. And I'm not going to go through this list of attributes on the left-hand side, but broadly, all these materials have been ranked on a scale of 4. Excellent being the dark green, good a lighter green, acceptable being the orange, and weak being red. And you can just see from the pictorial representation of this how the different materials compare on a relative basis. Now, to bring this to life, the next slide looks at 5 attributes in priority order. And there are 2 different examples here. And these are just chosen examples for this webinar. These are not brought together with any specific feature in mind. And what you have here is In example one at the top of this slide, life cycle costing, cryogenic resilience, energy absorption for safety purposes, recyclability, end of life, and corrosion resistance. And attribute 1 has a higher weighting than attribute 5, and the colour scoring from the previous chart, if something was described as excellent, it has a scoring of 4, and attribute 1 carries a weighting of 5, and you can see how the weightings move through the 4 or 5 attributes, I should say. So what this shows is that if those are your top desired attributes, the stainless pairing of austenitic and duplex score rather well. Fibre reinforced plastic is a little behind, and then aluminium comes bottom of that pack. If you change the attribute priority around and introduce a few different attributes, then the picture changes. So fibre reinforced plastic moves to the top, duplex stainless not far behind, and then a bit of a gap to the other materials. So this is very much the domain of material selectors, but it does indicate the importance of thinking about the attributes you want when considering materials. Thinking about 1 or 2 attributes or just thinking about upfront costs is not sufficient, I would argue. We're moving into a more complex world. We have to think in a more intellectual manner for our materials selection. But there's a bit of a narrative that needs to go with this when we consider mobility. And I think it's clear that from a mobility perspective, we want things to be light, we want things to be absolutely safe, and we want good physical properties of materials. There is no doubt composites have some excellent attributes in these areas, and they've been designed in that way to bring these attributes to the table. But modern-based iron alloys also combine the ability to have high strength and low weight, so become a really genuine competitor for some of the obvious lighter materials. It's equally fair to say, I think, that fibre reinforced plastic appears to have a conflicting duo of physical properties in that its strength is excellent, but its Young's modulus is really low. So you've got a bit of a dilemma there that does need to be understood before material selection. Equally, we can't overlook end-of-life recycling. Metals and alloys are fully recyclable, and they are easily segregated for that end-of-life recycling process, so you retain their value. Composites can be recycled, but present more challenges. Complex processes are needed to break down those composites into their component parts. And I think we have to take responsibility for cradle-to-grave processes. We can't just think about material selection, production of asset, and usage. We have to think of what happens at the end of life. So if we can't recycle easily, then I think we have to sort of revisit our material thinking. Now I'd like to move on and think about making and using hydrogen. And the chart on this page shows that really today we're looking at a production system that is relatively weak in terms of the use of renewable energy for hydrogen production, just 4%, which is really small. That is, of course, developing and growing, but will take some time and needs some initiative and some input. And there are many companies now who are investing in green hydrogen production. Of course, whilst there are many materials that can be used in the hydrogen production supply chain, we are going to look from this point onwards at stainless steels and their opportunities in this area. So let's start with electrolysis. So here the diagram is a very simple view of a hydrogen PM electrolyzer, and there are basically 4 big components here. The electrical power supply that we want to come from wind and solar energy, a supply of water, an anode or cathode, which are generally catalyst coated, and then a membrane that allows protons to pass through but not electrons. And this facility allows us to, from the power supply, break the water down into its component parts and generate hydrogen of one of the electrodes. Now, thinking about that, this polymer electrolytic membrane system, it is the leading technology for hydrogen production. It's not the only technology, and other technologies are present. But it's fair to say that when you look at the key elements of this, stainless steels do lend themselves well to the power plates, anode and cathode, primarily because they're non-corrosive. They don't require maintenance, so they're a very long life material. They are good electrical conductors. The coating with catalysts is relatively straightforward, and they can be made very thin, down to foil thicknesses. And as I've said, they're fully recyclable at end of life. When you look at other components of electrolyzer, stainless could be considered as coarse, but they're not the most, it's not the most appropriate material or material family to consider. And if we think about the stainless usage need, currently accepted guide numbers, which are based on a 1 millimeter thick set of power plates, portray a fact that 500 kilograms of stainless steel is needed per megawatt of power. And that is understood and rather agreed. However, there are two things that we need to recognise. The current trend is towards much bigger electrolyzers, 1 gigawatt plus, and that would require a very significant amount of stainless steel. So if the power plates could be reduced in thickness, and current aims are towards a factor of 10, that would require a 0.1 millimeter thick set of power plates or just 50 tons of stainless steel. And whilst that's still a significant quantity of stainless steel, that development is really now on the near horizon. So I think that's where we need to pitch ourselves for future guidance of stainless usage in electrolysis. But there's also ancillary plant when we consider hydrogen production system. And really, there are two areas to focus on. There's the upstream side. Before hydrogen production, the water that's coming in needs to be treated to remove salts. So, and that's through an ion exchange system. And when we talk salts, we're talking chlorides, carbonates, silicates, maybe some hydroxides. Those are the things we're trying to eliminate here. And there's a nice picture of a water treatment system on this slide. And stainless steels lend themselves well to this type of process, particularly chromium plus molybdenum bearing stainless steels, because when you have chlorides present, you have a particular corrosion mechanism called pitting corrosion taking place. And for seawater, you can calculate based on the chemical analysis a pitting resistance number for each different chemical analysis of stainless steels. The threshold for seawater that's commonly referred to in normal ambient temperatures is 22. So any stainless steel with a figure above that will work well in these sorts of environments. And what's known as a 316L austenitic stainless or a 2304 duplex stainless will perform really well in these environments. So whilst you could consider other materials if you want a tried and tested method that will give you trouble-free operation, I would argue that these types of stainless steel should be in your thinking. Then we can move on to the sort of, after hydrogen's been produced, the storage and refueling system. And once hydrogen is stored, before it can be dispensed, it needs to go through a compression system. It's buffered and stored in bottles, and it's cooled as well. And those three components of this total system is where stainless steels have a real opportunity. And here we have a hydrogen storage system shown in the photograph at the bottom here, but molybdenum bearing stainless steels are the most appropriate material for this low temperature, high pressure application. And that's because these type of stainless steels don't suffer from a ductile to brittle transition as the operating temperature falls. They are not susceptible to hydrogen embrittlement, obviously when storing hydrogen. They retain their strength and good elongation characteristics. They will provide with pretty much a maintenance-free operation, and it's a widely available product, one of the very common stainless products available all over the world. Now, if we start to try and put that into context, what does it mean in terms of volume? So if we consider a modular wind turbine hydrogen production system rated at 2.1 megawatts per hour, then for water demineralization, you would need around a ton of stainless steel. There's a bit of flexibility based on design, but it's something close to a ton of stainless steel. and that's in the pre-treatment and treatment segments of the system, where the water is still full of undesirable salts and minerals. And as I've said, a low carbon austenitic or duplex grade with molybdenum present would be a good material choice here. When you consider the refueling station, you're looking at more like 1.5 tons of stainless steel, and focus now on an austenitic grade to avoid that ductile to brittle transition that I mentioned. So if we wrap all that up, and I've not talked specifically about the vehicles, but it's well understood that the fuel cell vehicles need about 60 kilograms of stainless steel, not just in the fuel cells, but associated valves and pipework for the hydrogen delivery system. Then what you're looking at is an electrolyzer needing about 140 kilograms of stainless steel based on the thin power plates, 0.1 millimeter. A water purification and treatment system requiring close on 1 ton of stainless steel. A storage and refueling unit, about 1.5 tons of stainless steel, and then a much smaller amount for the vehicles. But if we now superimpose against that the global targets for 2050, what the world expects currently, or the economists expect, the growth in these particular units and vehicles is expected to look like over the next 29 years, then you can see the numbers there. And there's less of a need for water for treatment and purification, because you can serve more than one electrolyzer from a water treatment and purification system. And then you get, at the end, when you start to multiply those numbers up, the aggregated stainless weight. So over 29 years, we're looking at almost 35 million tons of stainless, which is a little over 1 million tons a year, assuming a linear development, which of course we won't see. And these estimates have been made a little bit more conservative, somewhere of the order of 15% conservative, to recognize that there could be a further reduction on power plate thickness and also the impact of recovery from the COVID-19 pandemic. So these are conservative estimates at this stage, but at least it gives some guidance number for people, excuse me, producing the assets and also supplying the materials. Now, if we move on and try and sum up the mobility sector development, I think it's fair to say, based on what we've seen so far, there is no perfect solution. There are several things that can coexist. I'll talk about that in a moment. We know that in our energy production sector, we are starting to decarbonize. But when we think about manufacturing, that will take some time longer to get through. There are some countries that are leading the way. I think, to highlight just a few, Germany are now close to 40% of renewable energy in its power mix. Japan is building the woven city, which promises to be carbon neutral. And in the remote Orkney Islands off Scotland, which is a research centre for both wind power development and tidal power development, they are moving rapidly to a hydrogen economy where all their vehicles, all their power supplies are being sourced from hydrogen from electrolysis. And I think it's fair to say that the mobility sector is really well placed, best placed, I would argue, to drive the shift to carbon neutrality. If we can make this work, other things will follow fast. I equally believe that fuel cell vehicles and battery vehicles can coexist, and we really shouldn't fight about which is better than the other. It's all about getting away from our reliance on fossil fuels, not saying, hey, my electric vehicle or my fuel cell vehicle is better than yours. That's where we just shouldn't be having fights and discussions. We should move away from the old technology to the new technologies. So in summary, I would like to say we've absolutely got to face up to our need to change in mobility and do it now. We can't be petrol heads. We can't continue, as exciting as it may have been, can't continue doing that. We can't keep polluting the earth just because we have a love of internal combustion engines and the thrill for some that they bring. 28% of our global greenhouse emissions is a frightening number, and it's getting worse. We have a solution in the form of hydrogen. It's one of the most abundant elements on our planet. We just have to split water. But we can harness renewable energy to make the hydrogen. And in support of making hydrogen, storing hydrogen and dispensing hydrogen, we have a very sound range of available and fully recyclable materials. And I would argue that stainless steels are a key material group for this journey. They're not the sole prime material, they are one of several prime materials that should be considered. So in conclusion, I would very much argue that we have gone too far with our McDonaldization of society. That combination of efficiency, calculability, predictability and control doesn't always work, and it leads to an irrational outcome in many cases. So we have to now join together with one voice, dump our reliance on fossil fuels, choose materials that have sound green credentials, and stainless steels are one of those materials. They have the lowest of all the emissions measurements of any metals and alloys, and over plastics and composites much lower too. We should choose renewable energy sources and we should push for it. And a question I'd like to pitch is, in terms of thinking reuse, recycle and reduce, do our children understand this better than their parents? And can those parents afford that our legacy at the end of our time on this planet is, we had a great time, but we killed the planet along the way? I think that's just not acceptable. So let's drive green. Let's embrace the philosophy before it really is too late. And at that point, I will stop and thank you for your attention and hand the floor open to questions. Joe, do we have any questions?
Yes, there have been questions that have come in during the session already, Tim.
Okay.
The first one is not really a question, but it's picking your thoughts. It says, in addition to the green energy for mobility, we also need to think about the materials used to make the automobile and how to make those materials in a green environment. Do you have any thoughts on that?
Yeah, I mean, I do, and it's very interesting when you think about making materials. And I guess many people in the audience will be familiar with the concept of additive manufacturing, or 3D printing, as it's fondly referred to. But that concept becomes very useful, not necessarily for body panels of vehicles, for example, because there are things that are better suited to mass production, or what's the traditional subtractive production. But when you get into absolute components, you know, I think we should turn our attention to not machining away materials to make things, but building them up. And that gives an opportunity to redesign. So I think the notion of things like lightweighting and being greener in how we produce things lies very much with thinking about how do we want to make these components using a more modern technology like additive manufacturing, and do it with metals and alloys and maybe ceramics, things that can lend themselves to this approach very effectively. And then the notion of a batch of one rather than mass production becomes really interesting, because what you're passing around is files rather than materials. You start with a common raw material and you build your component up from that. So I think there is a real opportunity there that becomes very supportive of this type of thinking as well.
Okay, thank you. The next one is on the water treatment that you were talking about. Why not use polymers?
You can use polymers. Of course you can use polymers. There's no reason why you can't. They will do the job. But the one thing that you have to remember with polymers is their service life will be significant. Well, there's more than one thing, but one thing that you should remember, their service life will be significantly shorter than stainless steel, and that's well proven already in the water supply industry. Furthermore, with polymers, you're more likely to get leakages. So the resilience of those materials in all operating conditions, whether that be contact with your incoming water supply or the external conditions, is not as good as that of metals and alloys. So of course, I believe there will be parts of the world where polymers can be sensibly considered, But if you want the fit and forget solution rather than the fit and fix solution, you should turn your head towards alloy materials more than polymer materials. I think equally, polymers are really aligned to the fossil fuel sector. So, do we want to keep supporting that as we move away from internal combustion engines? It's still another opportunity to pollute the planet, and I would argue that's not where we want to direct our attentions.
Okay, thank you. So far, there are no more questions coming in. If there's any questions, please use the question box and we'll ask it for you.
Yeah, and of course, as I said, Joe, people want to ask questions after the event when they have digested the content. And I know some of it may be a little provocative, but it was intentionally done that way to say there is a big issue here we need to address as a society. Just as a little aside, a question I got this morning, I think there's a big need for governments to really wake up to this and present the opportunities, both to allow the automotive manufacturers to drive the shift and also allow the consumers to make the switch. So I think there is a need for governmental support here dramatically to allow this to happen. And we should lobby for that as a group of interested consumers, associations, industry representatives.
Where do you see the role of duplex stainless steel given its susceptibility to hydrogen embrittlement?
Yes, and I think that's a really sensible question because, of course, it does have some susceptibility. And for me, in water purification systems, I see that duplex stainless steels have a real role and opportunity because you're not in a situation where you're containing hydrogen. So once you've produced the hydrogen, I don't see duplex stainless steels as a valid proposition. Austenitics are far more appropriate. But in the water treatment, because you've got the presence of molybdenum, you have a good pitting resistance equivalent number, so it will resist corrosion to a very good level. It's an excellent product in those situations. Because it's got very high strength, it allows lightweighting of the systems. So you can exploit some very good characteristics, but absolutely keep it away from hydrogen.
Thank you. Waiting for the next question.
Just while we're waiting, I'll just say that there is a series of appendices with this presentation that go into more detail on some of the features described. So everybody will get the appendices, and I'm sure people will understand that you can't go through all the content in absolute detail, but there is more background information to come on this.
Seems to have been crystal clear.
Which is always good. And time efficient too.
Yeah, that's true.
I will say, whilst the audience is still listening, it's no surprise that I'm focusing on stainless steels today, and you'd probably expect me not to do anything different. But I think we have to recognise that there are many material choices, and stainless steels aren't just one of many complementary materials, and it is about using the right horses for the right courses, as we would say in English. That you select the material that's most appropriate. But I think what is important is that we don't just look at upfront costs. The material costs are often in people's mind because they're visible and they're comparative. But the maintenance costs is really where all the money goes. And if you can avoid that, whatever you install will be a much better proposition than trying to look for the lowest upfront costs. I think that's a mistake that generations have made in our society. and it's time to rethink things. The notion of fit and forget should be at the front of our minds and not fit and fix. So I think that's an important message.
There's a question that has come in, Tim.
Yeah.
Will the automakers accept this concept?
Hydrogen as a concept? It's a really good question, because they have a fantastic industry built around the internal combustion engine. But I equally think, will the governments accept this concept? Because clearly there's a lot of income earned on the taxation of fossil fuels. So you have sort of two big bodies here who have a vested interest in internal combustion engines. But you have to say that fundamentally what should be at the front of everybody's mind is keeping people safe, protecting our environment, allowing people to have a fair and reasonable life, and not putting them in harm's way. And if we continue to pollute the planet, then we don't have a future. So the industries will die if the planet dies. So I think the message is really stark. We have to face up to the need to change. And it's no good for big executives thinking, hey, I've got a money-making machine here, I want to keep doing the same things. The dinosaurs didn't survive, and for good reason. So we have to evolve, and we have to evolve using our brains and not thinking about our bank balances. That's what we were given, and we should use it. So yes, it's a big challenge, and people have to wake up and recognize. But I think you look at pockets of automotive manufacturers now, and they're really pushing the hydrogen development, but we need them to push faster. And I think we need to push them. We should, you know, make them wake up and say, we want this too as users. We don't just want to be the Lewis Hamiltons of the world and race around 300 kilometers an hour or whatever it is. We want to do things in a right and proper way for our planet, our economies, and our future generations. So let's all push. Together we can be strong.
Okay, there's another interesting question that came in.
Yeah.
Which of the presented applications is most likely to go stainless, and are there any of them that can only go stainless?
Well, as I said, you've always got a choice. But when you're working with corrosive environments, so thinking in water treatment, we know there are many parts of the world where the salts in water supplies are quite high. And whilst you could choose other materials that are non-corrosive, and you know, I mentioned this in this presentation, fiber reinforced plastic, which has very good anti-corrosion attributes. When you're working with things like stainless steel, you bring other benefits too. So some of the modern materials don't have the proven longevity in service and the maintenance-free performance. And I would argue that certainly when you're looking at water treatment, stainless steels are tried, tested, and reliable. But there are other choices, of course, and that comes down to material specifiers and designers ultimately. When you move to the other end of the supply chain to look at the storage and dispensing of hydrogen, you're working with low temperatures, then I think you need a material that is absolutely resilient and safe. And I would argue in those applications, that's where stainless steel has a huge part to play, should be the material of choice. It's always difficult to say 100% you can only use this material, but I pitched the question, you know, would we choose today, knowing what we've experienced, to dispense with our stainless steel cutlery and live at home with rusty old cutlery or plastic cutlery each and every day? It's fine when you go for McDonald's or KFC, but there's something about a material that is inherently hygienic, reliable and safe that we enjoy, and we need to look at that outside of our home environment too.
Okay. Seems the questions have died out a bit.
Okay, that's fine. I mean, we're approaching the full hour, so we ran a little ahead of time in terms of the presentation delivery. I hope for the audience everything was clear. As I've said, you're welcome to pitch questions after the event as well. We'll answer everything. So if there are no further questions, Joe, I'd like to thank everybody for registering, for their attention, for listening. I hope I wasn't overly provocative, but I think this is an issue where many of us on our planet have some concerns and want to see a transition to a world that is fundamentally safer for us all. So if there are no...
Yeah, there's one more question.
Sure.
Who will pay for the total cost of an FCV system?
That's an interesting question, because I'm not sure I understand the term total cost without some more detailed explanation. However, I think we need, because we need to have the power generation, the green power generation systems installed, and that won't come cheap. The investment cost is not cheap, for sure. But there are companies out there wanting to do this at a faster rate. I think it needs some government support, for sure. So if you accept that there are some good government initiatives and support to assist with the building of the wind turbines or the solar systems for power generation, and also the electrolyzers, the government will want to, or governments will want to, recoup that money. And I'm sure, therefore, they will want to tax the hydrogen fuel. I think what we have to appreciate, though, is the hydrogen fuel cost, whilst it will come down as we produce more and more, particularly through the green routes, the mobility sector, because you can get around 100 kilometers of travel per kilogram of hydrogen, which is proven now today, the hydrogen cost can be, on a comparative basis, higher than that for gasoline, and still the cost of travel is very affordable to the consumer. So I think we have to recognize that we probably, as consumers using fuel cell vehicles, will have to pay a little more for our fuel on an equivalent basis, and that's based on an equivalence that 1 kilogram of hydrogen is approximately equal to 1 gallon or 4.5 litres of gasoline, that you will get more benefits in the driving range. So yes, it might be more to fill a tank when you go to the filling station, but then you won't go back to the filling station for a much longer period of time. So I think we have to keep things in context. But without a doubt, upfront, governments need to support this, because otherwise we won't move away from where we are today, and we'll just create more and more problems in society and add extra cost into our social care systems, our healthcare systems. So we're really about supporting one transition to save money elsewhere.
Yes.
Any more?
Oh, well, no, as a comment. The ultimate solution will be to reduce the production of private vehicles.
I think that's a great comment, and there is no doubt that that's a great ambition. But we are creatures of habit, and we've grown to be accustomed to a very personal, a very introverted way of enjoying life for many people in sort of developed economies. And it's very easy to say that, and it's as I say, it's a fantastic ambition. Are we going to do it, I think, is the question. Without what is referred to now as the 20-minute supply chain in our towns and cities, I don't think that becomes a reality. So if you can't walk from your house within 15 or 20 minutes and get everything you need in your house, people are not going to do it, I don't think. So the whole supply chain system that has become global and centralized in our world has to unpick itself and become very local and decentralized, I think, to support that ambition. So it's a great ambition. I don't disagree with the statement, but other things have to come to make it a reality.
Okay, thank you, Tim.
Any other questions? Well, I like that comment. It is, and it's one we should all hold in our minds.
Yes, we should. I think that the end of the session, we're almost 9 o'clock now. There were some excellent questions, some excellent comments. So yes, let's prepare for the 3 o'clock this afternoon. Okay, so thank you everybody for your dedication, attention, and for listening to me speak for an hour. It's much appreciated, and I hope you got some interesting food for thought on many levels from this webinar. Thank you, have a good day, take care, bye-bye.